In the last class, we learned about the definition of vector spaces. And in this class, what we'll do is we'll learn some more basics of vector spaces. We'll learn about linear dependence and independence. Then hopefully we'll be able to also cover the concept of subspaces. Okay, so that's the plan, and if time would permit, then maybe we'll also look at the definition of inner product spaces. So linear dependence is a concept essentially that comes from the more basic concept of collinearity or coplanarity that we have in geometry, which means suppose if there are three vectors, let's say OA vector, OB vector, and let's say OC vector. There are three vectors, and they are such that the vectors AB and AC are pointing along the same direction. So let's say if you look at the OC vector that you have here, is now we know that can be represented as, I think we had done it in the previous class, as a combination of OA vector and alpha AB vector. Okay, alpha AB vector. Now, so you can write this AC vector as alpha times AB vector, and so AC minus alpha AB is going to be 0, which means that AC is equal to alpha times AB, and then that gives you the concept of collinearity. That means the vectors AB and BC, they lie along the same direction, and also AC lies in the same direction. That's what you will get from here. So this means that the vectors AC and AB are collinear or linearly dependent. That's how we will define it now. Now, if we extend this concept, the same concept, to n-dimensional spaces, let's say we have a collection of vectors v1, v2 till vn. So you have n vectors for an n-dimensional space, and what we're doing is, let's say we try to form a linear combination of them. We say that a linear combination of these vectors, summation lambda j p j is equal to 0. Okay, so now this equation that you have, if you can write it for a given set of vectors, if you can write it using lambda j's that are not all 0, some of them can be 0, but not all of them are 0, which brings us to that concept of linear dependence. So then you would call, if this equation has solutions such that all lambda j's are not all 0, and there can be multiple ways that you can write it. That means there could be multiple solutions to lambda, in this case, not a unique solution per se. So you have, then you can call this set V1, V2 to Vn as a linearly dependent set. So in this class, we will denote linearly dependent. When we want to write, we'll write this as LD. This is how we're going to denote that. Short form for that. Okay. So now, which essentially means that one or more vectors can be written in terms of other vectors. So this equation with non-zero lambda i's or lambda j's essentially implies that you can form some Vj. Let's say we can pick one. Let's say V3 can be written as a summation of all the other ones, j equal to 1 to n, j not equal to 3, lambda something, let's say j vj. So we can write it in this form, one of the vectors. So that's what linear dependence means. Now, if you choose a linearly dependent set and you add more vectors to it, then again it will remain linearly dependent. So, let's say if you have a linearly dependent set and which is a subset because you've added more vectors to it, and I formed another bigger set of vectors, let's say v1 to vn, where n is capital N is greater than the number of vectors that you had taken earlier, which is n. So then the bigger set that you get by adding more vectors to it will also be linearly dependent. That's very clear, right? That sort of looks obvious concept. Now, if the set that you're looking at is not linearly dependent, that means you don't have any solution to the equation that you had pasted earlier, that lambda jvj equal to 0. There is only one valid solution, which corresponds to lambda j equal to 0. That means this equation is true only when lambda j's are 0. Only trivial solution, as we'll put it. This equation has only trivial solutions. Then, in that case, the set that you get, you call it linearly independent. We'll denote it by the notation Li. That's how we call linearly independent. When we want to sort of denote a set as linearly independent, we'll use the notation Li. So, okay. Now let's take up an example. Let's say, okay, you have uh, the 2D plane, x-axis, and the y-axis placed like this, and now you're looking at a point xi, yj. Okay. So now, looking at this equation in this form, let's say xi vector plus yj vector is equal to 0, and this is going to be 0 only when x is 0 and y is 0. That is clear. And this implies that I and j, I cap comma j hat, is a linearly independent set. It's a simple example for that linear dependence. On 3D, you can take I, j, k hat as the three vectors as a set of is going to form a linearly independent set, right? Now, interestingly, as you can note from here, that any subset of a linearly independent set will also be linearly independent. So, suppose if we from the set I, j, k hat, if we make a smaller set, and we look at the subset I hat, j hat, this is also linearly independent. So, to sum it up, a superset, a bigger set of linearly dependent set is going to be linearly dependent, whereas a subset of a linearly independent set will also be linearly independent. So that thing we keep in mind. Now, for a given vector space, you can keep adding, you know, and can keep adding vectors to a linearly independent set. Okay, let's say you are adding in a specific way. You had a set V1. We write it down here as V1, V2 are, let's say, linearly independent vectors. Now, if I add one more vector to this, add one more vector to this set, if I add one more vector, then I get the set V1, V2, V3. And so I can keep adding like this, right? I can keep adding. But will it be like, can you keep adding to infinity? Well, not for every vector space. That brings us to the concept of dimension of a vector space. So you can keep adding the number of vectors that you can add to the set before it becomes a linearly dependent set is a finite number for most cases, and it is possible that you may have an infinite vector space. So the dimension of a vector space is essentially the number of elements that you can have in the biggest linearly independent set that you can form for a given, of course, for a given vector space. Not for every vector space V, but for a given vector space V. So looking at, you can define the dimension of a vector space, and we'll denote that by 10 of V, dimension of V. Okay, so most vector spaces that we will deal with would be finite dimensional, but there are some infinite dimensional vector spaces, and I'm sure you can think of an example. A good example would be polynomials. So consider the set, uh, consider this set where you have the elements of this set are 1, x, x square, x cube, and so on. And by a linear combination of these, you can form a polynomial of this sort, right? Now, these, of course, these all these vectors also, these expressions also belong to a polynomial of degree infinity. But then you can form another polynomial of some finite degree by choosing some of these vectors and then by taking a linear combination of them. Now you can note that all these quantities 1, x, x square, if you go by the basic definition of vector spaces and fields and the way we had gone about them, they also uh, form a vector space, and these are essentially the vectors of that vector space. Each of these elements is like a vector of that vector space. One is a vector of polynomial of degree infinity. X is a vector of polynomial of degree infinity. Okay, and then you can form another vector f of x, which is a linear combination of these. Now, clearly there could be some doubts about what this, but these are numbers. These become number once you give a value to x. Till you give a value of x, they are still quantities which are not don't have a real number associated with them, right? But of course, x takes value from real or complex that you can define on separate. But in this abstract way, they are still they can be treated as vectors. So a linearly independent set with the maximum possible number of vectors that has been given a separate name. We call it a maximal set. The maximum number of vectors that a linearly independent set can have, we call it a maximum set. And let's say if we have v1 to vn as the set of vectors, then this is the number n that you will have will give you the dimension of the space. So this is the maximal set for an n-dimensional vector space. That's how you'll read it. Now, if we add another vector to this, let's say vn plus 1, you know this new vector that you have added, vn plus 1, to this already existing set will make it linearly independent because linearly dependent. Because if you could add, then the dimension of the vector space would be even bigger. That would be make it n plus 1 dimensional vector space. But it's an n-dimensional vector space. You cannot add one more vector and still have a set which is linearly independent. So as soon as you add one more vector, it becomes linearly dependent. And when you add that, when you say linearly dependent, that means this set that you have formed, when you write that basic equation that we had talked about earlier, now when you will form that equation, you can sort of pretty much say that the new vector that you've added can be written in terms of all the other vectors in this way. So it's a linear combination of all the other ways. So I may not choose to write this as v hat or something, but whenever you can just assume that these quantities that I'm using, like for example v, it's going to be a vector. So that means, and this vn plus 1 that we have chosen from that vector space could be just any vector that you could pick. So this could be any vector from, let's say, the name that we give normally to this vector space, let's say, is V, capital V. That's where we are going to use it in this course, let's say. Now, this vector of vector space V can be written in terms of V1 to Vn, and it could be just any vector, right? So that means this gives us a way of generating by taking a linear combination of the linearly maximal set of vectors from the maximal set, that you can make any vector, which means that you can generate the entire vector space V using these vectors. And therefore, we can call this set V1 to Vn as basis for the vector space. That means you can just, this vector space can be constructed from these vectors. The entire set can be constructed from these vectors. So this forms the basis. So a maximal set is a basis. So for a given basis of a vector space, we can sort of, so let's say we denote them by E1 to E to E1, E to En. This representation of a vector V is unique. Now, of course, the set of vectors that you've taken, V1 to Vn, and which you're calling as a basis, that may not be unique. But once you have chosen one basis, then the representation, and when I say representation, I mean these values of lambda j's are unique. Now to prove this, we'll prove it by contradiction. So let's say it's not unique. Okay, let's say it's not unique. That means you can write V as lambda j ej, and you can also write this as in terms of mu j ej. Now the lambda j and mu j to begin with, we are saying is are not the same values. Now we can subtract these two vectors, and then we'll get something like summation of lambda j minus mu j, where j is running from 1 to n, is going to be a zero vector. That's what it means. Now we know that E1 to En are all linearly independent. So since all EJs are linearly independent, and then we have seen that for if you have all vectors are linearly independent, then for such an equation, the only solution is that the coefficients are all zero. That means all lambda j's and mu j's are zero, which means all lambda j's are equal to mu j's, which means that the representation is unique. That's where we end. And this ends the proof of this theorem. Now, as I said, that the representation of a vector using a basis is unique, but the basis that you have picked may not be unique. Okay, so you can have different. You can have I hat comma j hat. You can also have some other, let's say I hat plus j hat and I hat minus j hat. Right? That can also be used as a basis. So we can choose any maximal set as a basis. This is the example that I was talking about. So for example, you can have I hat j hat for 2D space as a basis. You can also have this. Okay. So if we write a vector, let's say 3i cap plus 2j hat in basis of I plus j hat and I minus j hat, then let's say we'll just equate the two to solve for alpha and beta. And when we solve for alpha and beta, we get alpha. Of course, alpha plus beta is equal to 3, and alpha minus beta is equal to 2. So we have these two equations. You can add them up. When you add them up, you get 2 alpha is 5, which gives you alpha is 5 by 2. When you subtract, you get beta as 1 by 2. So this is the solution. So this gives us the representation in terms of I hat j hat. So a vector which was looking something like this now can be written as in the new basis would be written as 5 by 2 plus half j hat, where this I hat, capital I hat, is small I hat plus j hat, and the capital J hat is small I hat minus j hat. And the representation would be this 5 by 2 and half. So you can see that the same, this whatever we have been seeing as 3 by 2 can also be read by somebody else as 5 by 2 plus half. So whenever somebody gives you a vector, of course, you would like to know what basis that they're talking about. And somewhere so we have sort of this rule which says that normally what you will be using is a standard basis. So that means if you are written something like 3 by 2, then there would be a certain set of vectors that you would note as 1 comma 0. That's how you'll define them, and 0 comma 1. And this basis that you're writing, this new vector that you're writing would be a linear combination of these. Okay, in a very straightforward way. So we'll define something called a standard base for a given vector space. So in this case, it's clear it's going to be the standard basis is constituted by these two vectors, right? And if we use any other basis, then we have to clearly indicate what basis we are using. Now, for the polynomial space, also, you would have similar bases coming into picture. So now, let's say we had talked about this as a linearly independent set, 1x, x squared. The only problem is that in this set, you can keep adding vectors and you can have a degree sort of x to the power n also there, n plus dot dot dot, where n can go to infinity. For a This is for a polynomial of degree infinity, right? So this is a basis for that degree, infinite dimensional space, as we said, right? So now we can, let's say, take up an example. Instead of this basis, 1x, x square, xn, sometimes people use very fancy polynomials. One of the fancy polynomials that people use is Chebyshev polynomial. I don't know if you have heard about it. They are essentially, they look like this. So the first Chebyshev polynomial is 1, the next one is x, and the next one is not x squared, but it's 2x squared minus 1, which is, you can see it as a linear combination of x squared and 1. Okay, you can see it as that, as a linear combination of this. So of course the coefficients we cannot, if we are choosing coefficients as x or something, so you cannot see x squared as x dot x. That's something that you will have to stop seeing as. If you're seeing the polynomial space as a vector space, then you should not see this as x dot x. So this is x squared. Okay, it is evaluated as x into x, but it is x squared as a separate vector. That's how you'll see it. Okay. So now I think I can mention just one more thing here, that the reason, so when we say, okay, you have a polynomial p1x on the left and a polynomial p2x, and this equation is true for any x, right? If this equation is true for any x, then let's say polynomial x looks like a1 plus a2x plus a3x square, and the right side polynomial is essentially b1 plus b2x plus b3x square. So if that is the case, then we have learned that we can sort of equate a1 with b1, right? And a2 with b2 and a3 with b3. The reason why we do that is, you can sort of already see it coming. You can take this, you can write this equation, take it to the left hand side, you will get a1 minus b1 plus a2 minus b2x plus a3 minus b3x square is equal to 0. And now it brings us to the equation that we have already mentioned, lambda j vj is 0, right? So this equation is true when all lambda j's are 0, because 1 that you have here as a vector 1 uh, and the vector x and the vector x square are linearly independent, so therefore lambda j's has to be all 0. That means a1 is equal to b1, a2 equal to b2, and a3 is equal to b3. Correct? So now when we use Chebyshev polynomials as the basis, again you can use the same concept, because 1x, 2x square minus 1 are all linearly independent. Just a brief word about Chebyshev polynomials. Chebyshev polynomials are essentially solutions of this differential equation. 1 minus x square, this is d2y dx square, x times dy dx, plus n square y is equal to 0. So if your n is 0, then your T0x is 1 as the solution, the series solution that you will get. For n equal to 1, you will get x. And in way you can form a recursive relation. Of course, you can think of it as a nonlinear mapping, but then because it's not a linear combination that you're forming because you have an x sitting here. So you can write the polynomial of n plus 1th order as 2 times x tn x minus tn minus 1x as this. And therefore you can get the n plus 1 degree polynomial, as you can see. So if you want to write y for n equal to 2, you can say that it's going to be given by 2 times x t1 x, which is x minus tn minus 1x, where that will be t0x, this gives you 1, and then you get the vector 2 square, you get the polynomial 2x square minus 1. Similarly, you can see that t3 it can be written. So it's going to be 2 times x, 2x square minus 1 minus x, and that gives you 4x square cube minus 3x as the third Chebyshev T3 Chebyshev polynomial. Right? So that's about basis. Now we'll go to the next concept of subspace. So subspace is essentially, before we go to subspace, let's say we'll talk about this subgroup concept because it comes from there only. So the concept of subgroup means that you have, let's say if you had a bigger set like this, okay, and then this is, let's say, the vector space V that we're talking about, let's say. Okay. Now you have a smaller group or smaller set there with the same binary operation that we talked about. In this case, it can be vector summation. So if you take this subset and you can take any two elements from this subset, let's say x1 and x2, and then you do the binary operation between them. Let's say you write x as x1 plus x2, and that turns out to be that for every x1, x2 that is there in this smaller set, we call this smaller set as S, they are all of them are going to be the resultant vector x also would lie in the same set. So this is for all x1, x2 belong to this smaller set S. So this is a closed subset, okay? And this closed subset also satisfies all the properties required for a group. So this subset satisfies all the properties. So then we can call it a subgroup. Now vector space, as you know, that it's an abelian group, right? So a subgroup of that with respect to the vector addition. Only additional thing is because you are allowed to have the scaling with the field f, so that in addition to this property that the linear combination, this binary operation should give you a resultant vector which also belongs to the same set. You have an additional property that you can scale any of these vectors which are from this subset, and then the resultant lambda x1 would also belong to the same set. Okay, so scaling should also not take you outside this subset. Okay, so then you call this subset of the vector space V as the subspace. So formally you'll write it this way, that if two vectors, let's say U and V, they belong to the a subset S of V, then you're saying U plus V also belongs to S. Okay. The next property is the scaling one that we mentioned. If U belongs to S, then if you scale that vector alpha using the field F, then alpha times U will also belong to S. Another requirement is because identity element has to be there, and that with respect to that binary operation, the identity element will not change, right? So that means that 0 should be a part of this also. So that means every subspace will have the 0 vector. That comes because of the abelian group requirement that the identity element should be there, right? That's when it will be able to satisfy all the properties required. So 0 belongs to S. Putting together, you can call a subspace, you can call a subset as a subspace if alpha u plus beta v belong to S, if alpha and beta, of course, they belong to the field F, and the vector u and v, they belong to the set S. So together, you can write these three properties in this form. And then if these properties are satisfied, that means if this particular thing is satisfied, then you can call a subset as a subspace. Right. So for example, here we have an let's say R2 space. This is a real space. Let's say I hat and J hat. So you're talking about the entire real space, 2D space, is a subspace of a 3D space. 2D space is a subspace of 3D space. So we denote subspace by this symbol. Like a subset, we use the same symbol. For subspace also, we use the same similar symbol. So you can write this thing as the 2D subspace is 3D as R2 is a subspace of R3. That's okay. In the function space or polynomial space, you can bring in the same concept of subspace. You can say let's say quadratic polynomial is a subspace of cubic polynomial space, which is going to be a subspace of infinite dimensional polynomial, which is a polynomial of degree infinity. So a polynomial of degree 2 subspace is a subspace of polynomial of degree 3 is a subspace of a polynomial of degree infinity. So you have a concept of subspaces for function spaces. Okay. Now you can have list down the properties of subspaces. These are the three important ones that I've listed down here. So if U is a subspace of V, then the dimension of U would always be less than equal to the dimension of V. That's given because, of course, you can see that the number of vectors, linearly independent vectors required to construct this subset are going to be smaller than what would be required for the bigger set to be constructed, right? That is what gives us this property. The dimension of U would be less than equal to dimension of V. If it turns out that the dimension of U is same as dimension of V, then using the same concept of the number of linearly independent vectors required to express any vector in a given vector space, we can immediately see that U has to be equal to V. So if somebody says that U is a subspace of V and the dimensions are equal, you can immediately conclude that both of the vector spaces have to be equal. Okay. Then if you take 0 alone, then that also forms a subspace. Normally we'll call it a subspace of dimension. So dimension of this subspace is essentially 0, right? So this is also obvious. Now, just like we can do binary operations between subspace vectors of a given vector space, we can think of the, binary operations between subspaces, okay, which will eventually be defined based on what you do with the elements of these subspaces. But let's define some basic operations. These you already know, so we'll just list them down here. So these are what we're talking about are operations between subspaces. Let's say if U and W are subspaces of V, and we denote this by U is a subspace of V and W is a subspace of V. You can do something called union. That means, and the way you define this set union is the way you have learned it during your 12th standard right? When we are doing Venn diagrams and set and all. Same thing here, exactly the same thing. There's hardly any difference. U union W is going to be a collection of all the vectors U such that U belongs to the subspace V or U belongs to the subspace W. That gives you union operation. Then you can have intersection between subspaces. So U intersection W is essentially a collection of all the vectors U which belong to U, capital U, the subspace U, and which also belong to the subspace W. So that will be the intersection. Now, the sum of vector spaces, if you want to look at. So, when we define the sum between vector spaces, like this is summation of vector spaces is what we're denoting. Okay, and this is, we write it down here. This is summation of subspaces. Okay. So that is essentially collection of all the vectors that you obtain by adding vectors u and w, where u belongs to the subspace u and w belongs to the subspace w. Okay. A summation is called is given a more specific name, and it's called direct sum. The same summation that we talked about here is called direct sum if it satisfies one additional property, that the U intersection W has only one element, which is 0. It means there is no common vector between U and W except for the 0 vector. Then we call it a direct sum. And to denote it as a spatial sum, we don't just write U plus W. We write U, the subspace U, plus with a circle around it, W. So this is a direct sum. So if somebody writes this, it clearly implies that you have intersection W as only 0 vector. Now, the interesting thing about this direct sum is that any vector that you will form, which will belong to, which will be formed by adding two vectors from one from U and one from W subspaces, that will be a unique decomposition. Okay, that will give you a unique decomposition, and it has very interesting consequences when we talk about function spaces. But now, for now, I think we'll stick to the general definition of vectors. So, if you form V by U plus W, U will belong to this and this, and it's going to be uniquely written like this. If you want to decompose V into two vectors which belong to U and W, this is the only way you can do it. Okay, and as I said, in the function spaces, you would have very interesting consequences of this. Anyway, moving forward, let's take an example. We'll take an example of RQ, and the basis is a standard basis I hat, J hat, K hat, and then we form a subspace of that, which is R square, and we call it this is I hat, J hat. Now, to denote the these vector spaces using the basis vectors, we can sometimes use this symbol, which indicates span of the vectors I and J, which means anything that can be formed by a linear combination of these two vectors. Okay. So as I said, any set of the set of vectors that you can form by linear combination. That also sort of gives us the vector space V. So we can sort of say R square is same as span of I and J. Now, if you take two subspaces of R square, which is going to be, let's say, we pick I hat and J hat as the basis. So I should write it as span here. Correct it. It should be span of J. So W is span of J hat, and this subspace U is a span of I hat. Now both are dimensions 1. That is clear because there's only one vector which is constructing it, the entire subspace. Now, if you take U union W, then it's essentially a collection of all the points that lie along the x-axis. So, what is and all the points along the y-axis. So, all the points along I hat, all the points if you put together, that will give you, let's say, you can write it as alpha I hat. Okay, and also all the j hats. Okay. Right, so all these points that you have on the x-axis and the y-axis are elements of this new set, which is formed by union of u and w. Okay, right, that's union. Now let's do intersection. So we move to the next page here like this. So intersection would be only zero axis, right? Because this is your U subspace, this is your W subspace, and the intersection is happening only at 0. So U intersection W is only 0 vector. Now, if you want to define sum U plus W, then it's going to be a linear combination of any, you take a vector uh, of U and a vector of W, okay, and when you add them up, you get the vector alpha I hat plus beta j hat, correct? So that U plus W is going to be alpha I hat plus beta j hat, which for, and this is like for any value of alpha and beta, right? This is alpha and beta belong to the uh, are real numbers, any real numbers. So essentially, if you look at the points that you have in this set, U plus W are all the points that are lying in the 2D plane. All of them would be. And along, including the x-axis and the y-axis, you can choose beta is 0 or alpha is 0. So you would have all the points on the axis also. So the entire 2D space can be formed by, is formed by this set U plus W. So, right. Now we can denote it on a graph like this. So this is, as we said, your U. This is your W. This is the axis if you take. Okay. So now I can write indicating with blue is U union W. Okay. These are the points. Then I can choose, let's say, my point U intersection W is just 1 point, right? It's a zero vector. Now, this is essentially your U intersection W, right? Now, U plus W is collection of all the points on the 2D space. So I think I'll just denote by hatching the entire thing with red, let's say. And this red thing gives you U plus W. And you know that because intersection is just the zero vector, so you can write this as U plus direct sum. Correct? So now somebody would ask you, okay, like whether what are these whether operations when you have done operations between the subspace U and the subspace W, the final thing that you get is is a subspace or is it a vector space or it doesn't form a vector space, right? It may not, right? So it turns out that when you do the union, more than often, the union will not give you a subspace. Why? Because you take two elements from the set U and W. Let's say alpha I have you have taken and you have taken beta j. And when you sort of do the binary operation between the two, that does not belong to U union W because it goes away from the axis and that's not part of U union W. So it doesn't satisfy, as I put here, it doesn't satisfy the closure property. Closure property is not satisfied. Now, u intersection w is just a zero vector. In this case, you can see clearly it's a subspace, but it will always be like not just in this example, it will always be a subspace. Okay. In this case, it becomes a little more trivial, but you can show that u intersection w, and that will be a part of your assignment. So this u intersection w will be a subspace. Okay. If you sum u and w, you'll get alpha I hat plus beta j hat, and that will belong to u plus w, right? So this does form a subspace. This is a subspace. So the sum forms a subspace, intersection forms a subspace, union does not form a subspace. Okay, it's a valid operation, of course, but you should know what it means. So you cannot take u union w as a vector. You cannot treat it as a vector space. That's what we're trying to get to, because it does not satisfy the closure property. Okay. Now you can sketch the same concept on Venn diagrams, and we'll use Venn diagrams extensively when we talk about vector spaces, because at the end, what these are essentially sets with an additional operator, with some additional operations and all. That's so the basic. These quantities are just elements of sets, and then what you do with them is a separate thing. So to denote a vector space, it's best to use Venn diagrams, in my opinion. For example, let's say this is the set U, which is sort of spanned by I, and let's say this is a subspace W, which is spanned by J, and the intersection point is just the zero vector, right? Now, U plus W, if you want to write, it's going to be the entire. It's going to be the entire set, which is, you can think of it as R2 space. So this is U plus W. Now if I have to show you what U union W is, it's a different color. This is the green color that you're seeing. It's very visible. I will hatch it. Okay, this and this together forms U union W. And this is the zero vector, is essentially, as you can clearly see from the Venn diagram, this is U intersection W. So that's how we'll denote them. And I think I'll stop here. We'll talk about inner product spaces in the next class. So we'll stop this class here.